We can start? Okay. Okay, thanks. So here is my last lecture. So let us recap where we were. We were talking about the regularization by Krajkman or smooth Krajkman noise for QD Euler. And I just stated last time the main results, one of the two main results, and the strategy to prove it. But not the strategy I did not outline. This is what I want to do today. Okay, so let me recap the equation, which is the theta plus u times grad theta dt, and then there is plus. Don't remember if I used did I use this one, sigma over k or sigma k times grad theta Stratonovich dwk, right, equal to 0. Again, you can think that this is just, roughly speaking, v times grad theta, where v is the usual one, the usual Krajkman vector field, this is the distributional valued with the usual property, right? That this one, q of s, this is Dirac delta, and the usual q. And I go fast, but we have seen this many times. Okay. Okay, of course, u is just k convolved with theta, and k is the Biot-Savart. So k is just the gradient of g, where g is the green kernel of the Laplacian. Okay, g is, let's say, log of x. Okay. Right, so, okay, perhaps I didn't say, should at some points give the rigorous definition of solution, okay? And here I mostly referred, as though I don't not necessarily as h to the h minus valued solution. So theta is an h dot minus valued solution. Okay. If it is an h minus valued process adapted. Okay, for those of you who knows what this means, otherwise it's not so important. Okay, which is has the property that it is L infinity in time. These paths are L infinity in times h minus 1 valued. Okay, so means that we are considering L2 valued velocity. Okay, so h minus 1 values vorticity. Okay, times cap continuous with values in h minus 4. This is just a technical assumption because we need to make sense of, some sense it's, we need some form of continuity, some continuous to be in some space, p almost surely. And, of course, this equality is satisfied. Sorry, theta t equal to theta 0. Okay, then we have, of course, we have this equality here is satisfied okay, let me cheat here, let me write this. Of course, this is not right. dr minus integral 0t of grad theta r times dw. Of course, we want to write this as in Ito form rigorously. Okay, this is okay. So I can write this in Ito form. So this is Stratonovich integral. Remember, we can write this as an Ito integral. Sorry, an Ito integral, yes, plus the correction, which in this case is just C half Laplace theta, where C is just such that Q of 0 is C times the identity, right? And in this way, so this becomes just plus C half integral 0t Laplace theta r in the R, right? Okay, this one, of course, the question could be, and this was also something that we discussed yesterday, how to make sense of this when theta is, say, just h minus 1. Okay, here I'm very kind of, well, let's say sloppy, so to say, I just define this in the simplest way as the curl of the divergence of u transpose, right? So what we saw also in last talk. So this is always when defined is in L2, is in L1, okay, and then where it, yeah, sure, thanks. Okay, thanks. Yes. H4, so h minus 4. This is just a technical minus 4. And this equality, so some people, sorry, this is badly written. I should have written this way. Okay, the stochastic integral, of course. This is something. This is somebody asked me. In fact, how can I define this? Well, you can prove that you have the right integrability of these things. So this one is well defined as an h minus 4. This equality here. This is finite in h minus 4. Okay, so that's why we need h minus 4. Actually, it's without the dot minus 4. So it makes sense. This equality actually is an equality in h minus 4. It's just to make things properly defined. Anyway, so our main theorem last time, okay, of Michele and myself, is that, okay, so uniqueness. So if okay, don't want to write. Let me just write in plain words. Yeah, last time we saw the precise formulation. Uniqueness, pathwise uniqueness. Uniqueness, sorry, in LP, and the condition is that, let's say, with this condition that 3/2 less than P less than infinity, and the alpha smaller than 1/2 and alpha smaller than 1 minus 1 over P. This is the relevant condition, and actually for technical reasons we also need this one anyway, and also this one. Okay. Anyway, under these assumptions, actually this one is now well defined in terms of distribution, so you can define directly this one. Okay. Right, we have also a second result, okay, again by Michele and myself, okay, which is actually about existence. Okay. Okay, so alpha now can be any number in between 0 and 1, and theta 0 has to be in h dot minus 1. Then there exists a weak solution, weak probabilistic, I mean also analytically, but probabilistically weak solution in theta in h minus 1. Okay, and satisfying, in addition, in addition, that theta is actually L2 time and random variable omega with values in h, with the dot doesn't matter, minus alpha. Okay? Right? This is also okay, so the first result is about uniqueness in LP, and this we have seen is an improvement with respect to the deterministic theory. But then we have also this result of existence, which is also an improvement with respect to the deterministic theory. Why? Because if you recall, okay, we have, first of all, this is something that we see we started with something which is just h minus 1, okay, and we gain regularity, right? We go to h minus alpha, so there is a gain of 1 minus alpha regularity. So from minus 1 to minus alpha, so 1 minus alpha regularity in space, of course. This is something that you don't expect again for a usual continuity equation, right? Kind of anomalous. For continuity. Also, we have existence for every initial condition in h dot minus 1. Or in other words, for every velocity in L2. Oh, yes, L2 capital 1 perhaps. No, L2. Right. Right. And here, okay, the only comparable, so the result by Delort that was known, usually I had to admit something more on theta 0, like positive, and then it becomes a positive measures. But also, I mean, there is actually a comparable result, let's say by Wiedemann, using convex integration, but our proof is actually different in a way, in the sense that we are not using we are using a kind of, for existence, the classical compactness or a classical compactness approximation statement. So in particular, for example, we can sort of compactness argument, for which in particular we can also get a control kind of an inequality for the energy. Okay. 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 Okay, so these two are two results, two improvements with respect to the deterministic theory. Okay, let me also mention that there was a previous result, some months before ours, by Lucio Galeati and Dejun Luo. I'm not sure it's published right now, but it came a bit before ours, where they consider a slightly regularized version, let's say log Euler, because they slightly smooth the irregularity of the kernel by a factor log, okay? And they get, but they have to put a more irregular noise, and they get something different, which is, let's say, weak uniqueness. So not passwise, something weaker in some sense, right? And also they get, actually they get also something more, I should say. So for example, they get the equivalence, equivalence of the law with the linear Kragman model. You also get other results for hypoviscous Navier-Stokes and so on, but okay. And the method is quite different. It's based on Girsonov theorem. It's just to tell you that there are other results as well. Okay. Let me also remark another point, that even if you are not interested in Euler plus Kragman, but just in plus Kragman, this result, this regularity gain, as we will see, holds true also for Kragman itself. For no smooth, of course, no smooth. Kragman. Okay, we will see why. Okay. Particularly in this way, we will get another proof of uniqueness for Kragman, for in this class here, for the Kragman model, right? Yes, en passant, so to say. Okay. So, questions so far? Yes. I will show you why. It's a bit, in the end, it's an estimate, it's a style, kind of parabolic style estimate. I will show you why. Okay. Right, so let me explain you the strategy. Now, okay, let me say, I think I will mostly focus on uniqueness, right? Perhaps I'll say some words about existence later, right? But let me focus on the uniqueness result. Okay, first step. See if I didn't forget anything, let me just check. Okay. Okay. First step. Okay, we want to get this anomalous negative. So the first two steps are the crucial one in a certain sense, right? Anomalous negative Sobolev regularization. So we said 1 minus alpha gain in the, okay, for no smooth Kragman only. So what I was anticipating before. Okay, right. Okay, so the first point is that this Kragman model allows us to get a gain, an anomalous gain, in the negative Sobolev space, right? Okay. The second step, this is the other crucial step, is that actually this one, the same regularity holds for as well for Euler plus Kragman. Okay. Okay. And then in the last step, third step, we are going to get the uniqueness, okay, in LP, by essentially bounding. Well, okay, we will see. I mean, this is, but this is essentially based on kind of functional analysis, functional analytics tools. functional analytic. Analytic bound. Okay. Using the extra regularity. Using the extra regularity. Questions so far? Okay. So let's now see the proof and the steps. So point 2, kind of, let's say step 1, so anomalous regularization. Anomalous regularization for the Krajina. Okay. So let us go back one step to the no smooth Krajina, right? So this one, divergence of sum over k, sigma k scalar grad theta, no mu, we call it, sorry, mu Stratonovich dwk. Okay. Equal to 0. And let me rewrite also equivalently in ito4 as d mu plus divergence of sum over k, oh sorry, there is no grad here, of course, mu Stratonovich, sorry, ito dwk equal to, okay, the sum of course can be to the other side, but c half Laplace mu dt. Okay. Okay, so here comes the fundamental idea, or one of the two fundamental idea for Krajina. We have seen that the Krajina model splits particles, right? This split particles is what brings anomalous regularization in negative Sobolev space. And it does through the gain of integrability at the level of the particle distance. The idea is the particle splitting brings anomalous regularization in negative Sobolev through essentially equivalent to be a gain of integrability. Well, not really of the distance actually, but of, let's say, 1 over the distance in a way. Okay. Okay, so we see that this in time gains integrability, and so this brings the anomalous regularization. Exactly, how do we do? Okay, let us see the heuristics kind of first. Let's see some heuristics. Okay, we saw that two particles, xx and xy, get separated. Okay, so it is natural to think that if you are separating particle, so we expect. Let me write really in a very naive way, right? That the inverse of the distance of those two particles should get smaller, on average, at least. Because there is always a Brownian motion behind, so there are oscillations, but on average, since we have Brownian motion, we have separation, this quantity should get smaller. And so, it should gain integrability. Imagine, for example, you start with two particles that are at the same position, this is infinite, but then, as soon as you move on, this becomes finite, and it should become, on average, less and less smaller, right? Now, okay, this is a very naive idea, but of course it's not, I mean, one cannot prove things like with just this idea. So the point is that The point is that this can be explicitly verified thanks to the closed SD, 1D SD, for the distance. So we can make this really quantitative. Okay. Okay. How do we make quantitative? Let's take, okay, let us start heuristically with the Lagrangian viewpoint. Lagrangian, right? So the distance, right? Okay, let's take, rather than studying directly 1 over phi, I want to study now phi of ut, which is log of ut minus 1. Okay? So a mild singular function in 0. There is a reason why I took log. Some people of you perhaps have already seen. Of course, that's related to Euler. But anyway, to the G, right? Right? So, and now you can apply, by applying Ito formula to the SD for Y, which I don't write, one can actually get, at least formally, okay, the following things. Expectation of log of ut minus 1. Okay. So you start with the log, mild singularity, and you get minus constant, the expectation of xt, x minus xty, to the power minus 2 plus 2 alpha. Some constant which depends on alpha. Okay. So we started with the mild singularity, we get integrability of power law. Okay. Okay. This is exactly the quantitative statement of the idea that we had before. Okay. Okay. Let's make, so now we will see later on why this implies the regularity at the level of negative Sobolev space. Okay. The idea is relatively classical. But let's see this, how to make this rigorous, because formally, okay, yes, we argue with the two-point motion, but the two-point motion, I mean, at the level of the rigorous proof, we always work with the Eulerian viewpoint. Okay? Eulerian, rigorous computation. If you remember, recall this fact that I told you at least formally, you can connect the two-point motion, so the expectation of some function psi of xt, x, xty, you can connect to the Eulerian viewpoint just taking psi of x, y times mu t x in the x if you want. Sorry, mu now in this case is probably theta because it's theta t x, theta t dy. Let me write theta t x, theta t y, dx dy. Expected value. Hope you can read, right? But it was the formula that I saw, right? So considering this quantity essentially is equivalent to say, let us consider the expectation of the double integral of log of x minus y minus 1 mu t. Sorry, mu t. Yes, no, sorry, yes, mu t because so far, sorry. We are just consider Krajina, not Euler plus Krajina. Okay. Mu t dx, mu t dy. Ah, sorry. Of course, here I always missing here. Sorry, here there should have been mu 0 dx, mu 0 dy. Okay. Anyway, so essentially we want to compute this quantity here. Right? You can note, and that this is actually what is important, this is actually the function g. Okay, sorry, I think I've erased, but the green kernel of the Laplacian, this will play a role later. Okay, and so, okay, I want to do, now again it's a question of, now it's a PDE computation, right? Or SPD computation. Questions so far? Okay, so how do we do the computation? Well, you can take your favorite way. The plain way is just to say, in the end of the story, you know, this is a function, infinite dimensional function of mu, so a function of the infinite dimensional space. So this f of mu equal to just mu times g convolved with mu, where g is our this function here, the log, right? So it's just a question of applying the formula to this, right? For this one, okay. But this is very easy because it's just a bilinear form. This is so the derivative in the function phi is just 2 phi g grad g convolved with mu, and the double derivative is just phi psi is just phi g, sorry, 2 phi g convolved with psi. Okay. Right. Or I mean, yes. Okay, you have to take care, however, always of the second order term when you do these computations because of the Brownian motion. Right, and then let's see, okay, so the d over dt of the expectation of g, let's say, mu g convolved with mu. Okay, let's see if we can do all the computation. Okay, so on one side, so there is one term that we get. Okay, so first of all, there are the first order term of this form here, where in place of phi, I have to put what is in the left-hand side of the equation that I think I've written. No, this one, sorry, okay. Right, so this and this term here. So we have sort of, we have like C half Laplace mu, G convolved with mu. And then you have also minus, let's see, yes, no, sorry, plus, because now we integrate by parts. Or actually, let me write this way, minus sum over k. Oh, no, sorry, okay, this, wait a moment. No, sorry. Okay, there is this term here, dt, sort of, okay. Right, let me write without expectation. This, then we have this dt, then we have something minus something dw, which we will not care really, because then this expectation will be 0, we can forget. And then we have the second order term, right? Where we have to put in place of phi and psi, we have to put what is inside here, inside the stochastic integral, this term here. So this will be then, so sum over k of sigma k times grad mu, g convolved with sigma k times grad mu, dt. And there is, I think, a factor 1/2. No, there is no factor 1/2. Even here, there is no factor 1/2 because there is the 2 here. It should go with a plus. Okay. It's just applying the formula, right? If you are acquainted with that, you can do as an X. Sorry. Sorry, absolutely. Yeah, sorry. No. I think this should be fine, right? Because so far this is just a bilinear form, right? So it doesn't matter. Of course, we will get the second derivative here when we integrate by parts. So if you can view also as a test function testing against g, and then multiplying this equation by mu at some. But anyway, you can choose other ways. You will get some equation of this form, right? Of course, yeah. So now we can take expectation, and when we take expectation, the stochastic integral disappears, so we don't care. Okay, so this is just, I mean, these are standard computations. I'm not doing anything fancy, right? So this is just C. Okay, let me write now in a slightly, let me just integrate this by parts. So on one side we get, I recall you that C is just, C times the identity is just Q of 0. So let me write this term in a fancy way as a trace of Q of 0 d square mu. Okay, times G convolved with mu. Okay, plus the expectation of this one here, which is, right, I can perhaps already integrate by parts, so here I get a minus. This one gets the trace of sum over k of sigma k, sorry, perhaps I can write this way, so this is sigma k mu d square g sigma k mu. Okay, in some, okay. Now let's see. Okay, of course I can here as well integrate this by parts twice and bring it on G. So let me do this. I hope you can will forgive me for erasing this, but this is just an integration by parts. Okay, now you start seeing, if I now sum this, it should have been sum over all k. Right? Yes. Here, so okay, these one are always divergence free, so I can always say that this is divergence. So one of these divergences goes as a gradient of here, keeping in mind exact the indices about differentiation, which I will not do here, and the other here you integrate by parts. So you get the minus by integration by parts, and you get d square. With the right indices, which I'm not writing at this point, but if you are careful, you can. Right? Yeah, it's absolutely a standard computation that as soon as you are acquainted with the formula, you know what to do. Okay, there's nothing fancy. Okay, but anyway, what you come to is the following formula at some point. If you put everything together, and this is the main point, the trace of q of 0 minus q times d square g, which is the main things, convolved with mu. Let me write this, yes, convolved with mu, and tested then against mu. Okay. This is the term, this one. Right. Okay. Now let's compute what this term does. This is also a computation well known, right? Since even the first paper from Kreisman, I think something similar was written. Again, it's just something standard. But let's see. I mean, at least for a generic G, I'm not sure. I never see this with the logarithm, right? Right. So let's see what happens if we plug in. So far, we have not used the exact form of G. You can take whatever G you like. Let's take G, which is the log. Okay, and then the grad G is just standard computation. This is x over x square minus, and here there is the square G of x, 1 over x squared, just standard computation, ignoring the singularity, qxx orthogonal over x squared. Yes? No, yeah, sure. So you're right. Thanks. Convolved with, absolutely. Thanks. Okay. No, sorry. Yeah, absolutely. Okay. Now you plug into this term into this equation. It might be a bit boring, but again, this is just computations. So q of 0 minus q of x times d square g. I don't want to do the full compute. I don't know why I wrote this, but anyway. Now it's just a question of exercise. Sorry, perhaps one thing that I should recall, otherwise the thing is incomplete. Let me recall here that for q of x, you have a quite precise form, which is ql of x. Actually, let me just write directly for q of 0 minus q of x. This is just nothing but beta L of times x to the power 2 alpha, xx orthogonal, xx square, transpose, x square, such as the projection over x, or the direction x, plus beta n, x to the power 2 alpha, the projection on the orthogonal direction to x. Okay. Right? And now, if you plug in everything into this formula, this is just an easy exercise, you get that this term here, this trace of q0 minus q of x times d square g of x. Okay, you just plug in everything and you get the following. Okay, so first of all, okay, let me write the formula and then we see. This is 1 over, this is x to the power 2, minus 2 plus 2 alpha. Okay, times, okay, these are here, there should be lower order term, which I will forget here. Then times beta L minus beta N, okay, plus lower order term. I think I forgot something. No, it's correct. Okay, first of all, this power here you can kind of get easily by homogeneity. This is power 2 alpha. When we differentiate the log, we get the power minus 2. So easily we get minus 2 plus 2 alpha. Okay? And here you see that something, so if alpha is where, in the regular case, you would just get alpha equal to 1, this would be 0. But here you get a negative power. That's the key. But here, let's see this, of course. The sign will matter. And so here we will use the relation between beta L and beta N, which I recalled you, it is that beta N is just beta L times 1 plus 2 alpha over D minus 1, which in this case is actually 1. Anyway, this is larger than beta L. Okay, so you see these things as a minus a constant times x to the power minus 2 plus 2 alpha, plus lower order. Importantly, these things is negative. So all what we get by the way, we are not using anything of what we said before, almost anything apart of the form of the Q of the Kraken, right? So even if you didn't understand what we did before, you see these are just a computation of the model. So all what we get is the following, d over dt of the expectation of the log x minus 1 mu t dx mu t dy is equal to minus constant expectation of integral of x minus y to the power minus 2 plus 2 alpha mu t dx mu t dy. Plus lower order term, which I will forget. Okay? So exactly the Eulerian computation, the Eulerian this computation, this formula here in the Eulerian coordinate. Okay. Okay. So this is the first bit. So we saw that we get, and the important thing is the minus, right? So if you want, in other words, I can write this plus, okay, and then there is something which is under control. So something that, let's say, I can bound with 1. Up to 1. No, not 1, but something that I can control. Right? And so you see, we get a control L2 in time and omega. That's why we get, right? Because this is okay. Well, we will see in a moment, but we get the control of this term here. Okay, why? So gain of integrability done, fine. But what has to do with negative sublet space? Those of you who know this space, so probably many of you have already perhaps seen what I'm going to see, what I'm going to do. So the point is that, it's very classical, this G is the green kernel of minus Laplacian, and so of course this is nothing but, so mu t, I recalled you this is G, mu t G convolved with mu t is nothing but the h dot minus 1 norm of mu. And what is about this? Let me call this up to a constant G1 minus alpha. G1 minus alpha is the theory of risk potential, is the green kernel of minus Laplace to the power, let me get the power right, alpha. Okay, so in fact, and so mu t G alpha, 1 minus alpha convolved with mu t is actually up to a constant again, 1 h dot minus alpha square. Okay, so this is if you want. And so what we get is that d over dt, the expectation of mu t, h dot minus 1 plus constant expectation of mu t, h dot minus alpha square is bounded by, let's say, lower order. So this is why we get the L2, right? Because L2 in, if we integrate this in time, this is L2 in time and random variable, right? This is what your question was. Fine, so here we go with the gain of integrability. Gain of negative subreferability. Okay, So you see this actually, I mean, the fact that we get exactly this gain is due to the Kraichnan. However, this is relatively general. So as soon as you are splitting, you should expect some kind of negative Sobolev, some negative regularity gain. Negative Sobolev regularity gain. Some comments. The lower alpha is, so the lower your field is, the higher you gain, right? Which has some analogy with what you do also in finite dimensional space. Unfortunately, we didn't see, but you can actually take a fractional Brownian motion, and the lower the fractional index is, the higher you gain, something similar philosophically. The other thing is there are some technicalities to do this computation because, okay, I said I did everything formal, but of course G is singular, so I should have been more careful to do this computation. You can, of course, smooth and so on, and this is relatively standard. Okay, one I will not do, but this is relatively standard. What is slightly annoying, actually a bit annoying, are these lower order terms, because I say, yes, they are lower order, but they are lower order in physical space. While I would like to have lower order in Fourier space, because in the end of the story here, I want to pass to the Fourier and use the Fourier analysis. And this causes a bit of trouble sometimes, right? So it was not, at least for us, it was not easy. It's not too difficult, but in a way. Right, okay. Questions so far? One thing that you may notice here, perhaps it's worth noting, is that this is a kind of like fractional parabolic estimate. So it's a bit, it acts, in this case, the Kraichnan acts a bit like a Laplace to the power alpha or alpha alpha. No, I think it's alpha, whatever. I mean, perhaps 1 minus alpha, something. I'm not sure about that. This is true. This is something that you also see, and it was written in literature, in the couple of papers at least, for the two-point motion, for the regularity of the two-point motion. And nonetheless, let me say that you have to be, I mean, it's not that the Kraichnan model is a fractional Laplacian, okay? But both because it is a continuity equation, okay? We are just adding non-smooth in time and space and so on, but we are just adding a vector field, not a Laplacian, whatever power. And also, more seriously, also because actually, you don't expect that such regularity gain to get up to a threshold, certain threshold. And actually, you expect that a smooth vector field to be deregularized, to lose regularity. This is, okay, let me say it a bit fast, but if this were not the case, then the solution of the Kraichnan field mu would be renormalizable in the sense of Di-Perna-Lyons, and then you could infer, and then you would infer conservation of LP norm and so on, which you don't have, right? You don't have because there is this splitting, right? So, okay. Anyway, let me thought up for the normal. So far everything was for Kraichnan, but what about Euler plus Kraichnan? Okay. So, okay, I just write the equation once more, but this is just plus some of the sigma k times theta, dwk. Actually, well, okay, this one, u, okay, and k is the orthogonal gradient of the Laplace. I think that many of you have seen already what happens. This is the second important idea. Somehow, the idea is that the nonlinear, so here now we have to care the new things with respect to the Kraichnan is the nonlinear drift, which might be complicated at first, but in this case it is not, just because the nonlinear drift, u times grad theta, preserves the energy, h dot minus 1 norm of theta, which is exactly the energy, okay? And so all the computation that we have done just goes through because the contribution of the drift goes away. In fact, I can show you very briefly, but if you take now the expectation of theta, you just try to do the same things, right? Okay, you get the drift will contribute as usual as the term u times grad theta, g convolved with theta. Okay, plus the terms from the other terms that we have seen just before from Krajkman. Terms from Krajkman. Okay, so this one, this is okay, so the terms that we have all computed there. But this one, of course, this is nothing but, I mean, you can do all the computations. I should say this is, should be, I mean, it's been also shown, I think, more than once. This is just the energy, the contribution of the drift to the energy, which is just here. If you want to see it explicitly, let's say, just say you integrate by part, and you see this is just grad orthogonal G convolved with theta times theta against grad G convolved with theta. These, of course, are orthogonal, and so this one is just here. Just the classical conservation of energy. So no contribution from this term, and you get exactly the same equation. Sorry, plus theta t. Bounded by lower order term. Okay. Fine. Okay. And then we are almost done for the uniqueness. Let's now do the final step. Now the final step is essentially analytical. Third, no, fourth, sorry. Uniqueness in LP. Right? That's the conclusion. Okay, of course, let's take theta I solution to Euler plus Krajkman. Okay, I equal to 1 and 2, and let's take theta, which is the difference. We want to show, let's say that theta 0 is equal to 0, so they start from the same position. We want to show, of course, that theta is always equal to 0. Right. Okay, which equation does theta satisfy? So the idea is basically, okay, let's see the equation, satisfy theta. Theta satisfies the following equation. Okay, there we have so when we subtract the two equations for theta I, we get one term, the nonlinear term will contribute with two terms. This one plus k convolved with theta times grad theta 2 dt. And then, since the Krajkman noise is linear, this would just be grad theta Stratonovich wk equal to 0. Okay. Okay. And then the idea is just the following. Okay. To bound contributions. Yes, I think I can just say in word, perhaps. Okay. Okay. Well, let's see. After I see, I think it's easier if I just show. Right. So, okay, one of the two terms. Okay, now let's estimate again. Just functional analysis right now on. We using the extra regularity offered from the Krajkman, so even by the Krajkman square. Let's do again once more the computation. Now this is the difference. This is a bit like what we saw for the Krajkman or OS plus Krajkman, except that we have two terms here, right? These two terms here. Okay, so let's see. Okay, -1. If you do computation, this becomes G convolved with theta. Grad orthogonal G convolved with theta 1 against grad theta minus 2, the expectation of G convolved with theta, grad G convolved with theta, okay, grad theta 2. Okay. Plus, then the noise contribution, of course, will give us actually minus constant times the expectation of theta t, theta to the power h minus alpha to the power square, plus lower order term. Just standard computations, right? Okay. Now, okay, this one is the contribution of the, this one is the contribution of the. Now, I guess you have seen what happens. One of the two terms, this one here, as for the conservation of the energy, this is just zero. Integrate by parts and use the conservation of it. This is just the conservation of the energy. And the other one, I think I don't, we are all tired, so perhaps I just give the estimate, but believe me, this is just functional analysis, nothing particularly fancy. Okay, you have to be, if you want, of course, I mean, if you want later on, I can show you after the lecture more in detail computation, feel free to ask. So this is just, it can be bounced by theta to the power h minus alpha square times theta 1 LP, L1 cap LP. Okay. Here, under the conditions that alpha is controlled by 1 over 1 minus p, and alpha is smaller than 1 alpha. Yeah, okay. This is where these two conditions appear. This is essentially control on the product, and then Sobolev embedding. Okay. It's not much. Right? Okay. And then, okay, so now, of course, you can see what, so this one is now uniformly controlled, because I have a control in L infinity of the, so perhaps I can cancel here. Okay. So now, so what we find is that the d over dt, one thing I want to say is that omega we have assumed, well, in the class of uniqueness, but that this one, if you want, is controlled, say, uniformly in time and omega, right? Uniformly in time and omega. Of course, you can always, I mean, when you know that there exists a solution, you can just say this is just bounded, let's say, by omega 0. Like, sorry, theta 0. Theta, yeah, sorry, because I have theta, yes. Theta 1, yeah, sorry, because it's one of the two solutions, theta 1. Okay, uniform in time. Okay. So this one is essentially up, we can forget, and then what we get is that d over dt of the expectation of theta t h minus alpha square bounded by contribution of Krajkman minus constant times theta to the power minus alpha square, and then the drift, which contributes with this. Okay. Now, of course, here you are not happy if this constant c is smaller than 1 with the, well, there is some other constant, let's say c tilde. You should, okay. But what you can do, and I guess if you are acquainted with the functional analysis tools, okay, here this is okay, in the equality, this is the critical case. If you are in the subcritical case, you play with delta and epsilon, and you get here something, let's say something smaller than C alpha, right? These are again a bit standard function. I mean, even if you don't know, I mean, this is relatively standard, so believe me, there's nothing particular there going on there, right? And then this one, then you get what you. So this is, say, bounded by minus, let's say, lower order term. And then by just a Gromwall argument, Gromwall lemma, you get the expectation. Sorry, minus 1. Sorry, here it should be minus 1. Theta t h minus 1 square is just 0. And then theta must be 0. End of the proof. Okay. Question so far? So let me recap. The main point is there is the take-home message, even if you didn't get all the computations, is that the Krajkman model gives this anomalous splitting. The anomalous splitting gives an anomalous regularization in negative Sobolev space. Okay. This one, because of the conservation of energy, right, goes through also in the nonlinear case and allows then to control, to close estimates in the case of for Euler plus Krajkman. Okay. That's more or less. Yes. Yeah, I'm coming to this also. Let me say this is, you can also, no, okay, so this I'm going to say later on. Okay, perhaps one word about existence result. The existence result goes by compactness, so you take some regularization, let's say theta delta solution to a regularized version, regularized version of Euler plus Krajcman, okay, in parameter delta, and then you want to have the convergence of theta delta. When you just have the solution, remember in this case the solution, we start just with an H-1 initial condition, so in this case, of course, we can show that the energy is preserved, but no more than that. So in the deterministic case, you would just have that theta delta H-1 is preserved. So it's, yes, bounded uniformly, and so you get convergence weak in H-1, or if you want, velocity converge weakly in L2. But in this case, the Krajcman case, so plus Krajcman, of course, since we get the control over H minus alpha norm, of course integrated in time, and this, okay, this we can actually get convergence strongly in H minus 1. And this is the key because this allows to pass to the limit in the nonlinear term, which is exactly what fails in general in the deterministic case. I didn't spell all details, but there are certain other estimates that one has to do to control this uniform mean time and so on, which might be sometimes a bit complicated, but the key, more technical rather than complicated. The idea. Okay, questions so far? Okay, I think I have 20 minutes, so let me perhaps just say some other developments that one can do. Just the statement, perhaps a couple of words about the idea. Okay. So further development. Say this would be kind of a, if you want, a fifth chapter, but however, further development. Okay. So first development, you saw I took the H minus the expectation of the H. Let's go back to Krajcman itself, right? Okay. Then you have seen we have estimated the expectation square of the H minus 1. But why we chose the H minus 1? Just because, just in order to make this, to use the conservation of energy in Euler. The choice of the log, or if you want, of the H minus 1 norm, was not per se important for Krajcman. So it's kind of reasonable to expect that if we start from H minus S, okay, for some S, now we are in any dimension, so in any dimension B larger than Q, not necessarily in 2 dimensions, so this partly perhaps answer. For technical reason, let's take it S larger than, smaller than T over Q, because in Fourier otherwise this is a problem. This one, we should get, it's not so unreasonable actually, to get these things. Minus S plus 1 minus alpha. Right? With kind of similar computations. Oh, no, okay. So, how can we get to this? you can try to do similar computations, right? Heuristically, you would get heuristics as before, okay? Except that, well, it's not really for any s, for s such that s plus alpha minus 1, this index here, minus this index here, is larger than 0. Right. Why? Because if you accept, so we won't cover exactly all this threshold. In particular, we cannot go for s very close to 0. Okay, it has to be large enough, larger than 1 minus alpha. Because otherwise, when you do you remember here I had some green kernel which was minus d plus, I think here is what? This should be plus 1 minus, okay, here I have to be careful, 1 minus s minus alpha, I think with times 2, something like that. And so this is integrable as soon as this quantity is positive, right? No, perhaps it's the other way around. Okay, I mean, the right things, right? Okay. And then, so of course, when you exceed this threshold, this computation has problems because this becomes non-integrable. But you can do this in Fourier, right? And in Fourier, then it boils down to compute the Fourier transform of the term Q0 minus Q of x times d square g. This can be done. I didn't know how to do, but I asked Francesco Grotto and said, yes, it can be done, and indeed it can be done. So then we worked with Francesco, with Lucio as well, and okay, myself, most contribution I should say by Lucio and Francesco, this is paper which appeared this year, where we get essentially this form here for any s arbitrarily close to 0, right? So almost at 2 in a certain sense. And so in particular, you see, the point is for when this quantity, sorry, this I should have mentioned, when this quantity is negative, here you get this quantity becomes positive, and so it means that we gain positive Sobolev regularity. Okay? Gain of positive Sobolev regularity. This could also be, yes. Yes, for Euler plus Crichton, you mean? This was exactly the second point, yes. So, right, okay, so let me say, this one can do. This could also be related, if you want, to some mixing, because as was mentioned in one of the previous talk by Laszlo, this h minus alpha norm, h minus 1 norm have to do with mid-sense. So we are not able to give a decrease of the h minus 1 norm because of the lower order term. There is a nice paper about the smooth Crichton by Michele Cotizzelati, about that, Cotizzelati, Theodor Rivas, and no, Gvalani, sorry. I think it's published this year. Anyway. Okay, another thing, and this was exactly what was mentioned just one moment ago, okay, is about regularization for SQG. So if you want to, regularization for SQG, generalized SQG. Okay. Now, if we modify this to be, let's say, let me call K beta, with this being the green kernel of, now I don't remember, but it should be, let me see the convention that we have. Okay. The convention that we have is this one. It's just a question of indices things properly. This should be yeah, exactly. So it's the orthogonal gradient of minus Laplacian to the power minus 2 plus b over 2. Just a, I mean, everybody, I think, I mean, I'm not sure this is the one that we used. I'm not sure it is completely standard. Right. This is the green kernel of distinct terms here. Right. So let me say for b equal to 0, in our convention, just to understand, b equal to 0 is Euler, QD Euler, and b equal to 1 would be the true SQG. Okay. Also, I mean, all right. So I know that, for example, for SQG, the nice things about SQG is that well, nice things is that as far as I understand uniqueness, I asked also to some expert here, SQG, there is no, even a generalized SQG except Euler, there is no uniqueness result, right? Not even there is no kind of Udovich type result. In Vichy, yes, in Vichy. Yeah, okay, exactly. And there has been also works in the convex integration, as you perhaps shown in the viscous case at least. I'm not sure. Okay, perhaps right. And so what we have shown, but even before us, Yao and Dejun-Luo. This is a paper of Yao. Dejun-Luo, and then also in 2014, and then after we came with a slide with a more general result, my PhD student Marco Bagnara and Lucio and myself. We have done a similar uniqueness statement, uniqueness for generalized SQG. I don't want to write the full, there are certain parameters, condition under beta and alpha. Let me see if I can write it briefly. So the condition, I mean, okay, I'm not sure the condition here, it matters too much to write the condition. Let me just mention that we can catch for a suitable alpha, all beta between 0 smaller than 1 for suitable alpha. Okay. Unfortunately, not SQG. Not the one to. Minus, perhaps I was wrong, sorry. Yes, because, okay, for beta equal to 1, it must be, no, sure. Thanks. Yeah, thanks. Okay. No, in fact, sorry, it's, yeah, because I've written, yeah, it was minus 2 plus b, yeah, okay, yes. Minus, let's say, minus 2 plus beta. Okay, thanks. Okay. Sorry? What, yes, sorry. Thanks. Okay, it was a bit fast. Yes. Okay. And last point, then I stop. Just an ongoing work that we are doing with my PhD student, Marco, then Francesco Grotto, and myself. In some sense, ongoing. We are tackling the case of Kraichnan with stretching. Okay. Yeah. Which is the case, okay, it may sound like, I mean, it's not an easy generalization because when we have stretching is something of the form plus, let me write informally, grad V, or actually minus grad V times grad, solution times grad V, mu times, okay, mu times grad V, sorry for this. Okay, and so this V is already irregular, grad V is even more irregular. So it's unclear that this can ever, one can ever define the solution, right? We have some positive indications so far, but okay. Right, and so yes, we think for a moment. Right. Okay. Right, so this essentially, I think, okay, I have 10 minutes, but I don't think it's worth using them. Okay, so let me just perhaps stop for a moment and recap what we have seen. So we have seen that if you add, in some sense we have seen the effect of some form of noises on the PDEs, on ODEs and PDEs. We have seen first that if we add a noise, we take a nilpost PDE, think of the Peano phenomenon, post ODE, sorry, think of the Peano phenomenon. Then you can add a noise, just a classical Brownian motion, and you can get well-postness. You can restore well-postness, right? And this you can do also at the level of the corresponding continuity equations, right? And then, okay, so then we have asked ourselves, okay, can we do something similar for the nonlinear PDE? I concentrated on two-dimensional Euler. Then we said, okay, no, this is not really possible, not easily possible with the smooth noise, or perhaps it's possible, but we didn't. At least the computation that we did with vortices suggested that we had to use a no smooth noise, and this led us to Kraichner noise, which is an object of interest on its own, and I hope that right. And and we have seen for this no smooth Kraichner noise several surprising features, like uniqueness and at the same time splitting of particles. Also anomalous dissipation, I've mentioned anomalous dissipation and so on. And then we have seen that this actually is related to regularization today with a regularization effect, a gain of regularity at the negative and actually even a little bit positive Sobolev regularity. And this can be used to have indeed regularization by noise phenomenon for two-dimensional equation. So I hope you have found this interesting, even just a part of that. And if you want, so I'll stop here. If you want, I'm here for the rest of also for the next week, of course. So for the whole next week. And so if you have any question, don't even whatever about the course, don't hesitate to ask me or even discussion. I'm happy to do. Thanks. If there are any questions, please. Yes, SQG. Sorry? Yeah, 2D. 3D, I mean, the thing is, okay, in a way, in 3D it would be nice to add the stretching. Because the stretching is, in 3D, if you write the vorticity equation, you have the stretching, so that's why we like. But on the other hand, the result that seems to be true in this case here is for two irregular vector fields, so I'm not sure it's going to be of help. I mean, I think it's interesting on its own to define Kraichner for this with stretching, but I'm not sure it's going to be of any help for 3D Euler. I think I can stop here. No further questions. Thank you. Let me say, I want, of course, to thank the organizers again for the opportunity of being here and giving this